Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at Chapter 3 out of the Dahm and Visco textbook on thermodynamics, which is material and energy balances. And in this lesson, we'll be looking at a heat exchanger. As a reminder, for steady flow processes, our first law of thermodynamics, or our energy balance, is that the sum of the flow energy out minus in is equal to the heat transfer in and out of the system plus the shaft work in or out of the system. So let's discuss this example. It says that a steady-state heat exchanger is designed to take in cool air and circulate it over tubes containing steam. The air is thus heated, and the steam leaves the exchanger at a lower temperature than it entered. Steam enters a particular exchanger at 2 bar and 200 degrees C, while the air enters at 35 degrees C and leaves at 45 degrees C, and those enthalpies are given. So what a heat exchanger is in a very simple-minded sense, we'll just consider it like a black box, is it basically has two different fluids that flow through it, but they are maintained as separate streams throughout. So in this case, we have air that comes in at a cool temperature, in this particular case, 35 degrees C, and then that air leaves at 45 degrees C. We also have steam that enters, and we'll just have it enter on the same side because best practice when you aren't really trying to describe the process itself with our little box and arrow diagrams is to have feed enter from the left and product leave from the right. Literally, the way this would be built is probably that they would enter on opposite sides. But so we have H2O, and it enters at 2 bar and 200 degrees C, and the water leaves at 2 bar, in other words, the same pressure, and a temperature that we don't yet know. Okay. We have the enthalpies of the air going in and out, and we know that there are 50 kilograms per minute of air. And we know that this is a saturated vapor. Okay, so the quality at the exit is going to be 1 if it's a saturated vapor. I have really, at this point, written down in symbols this problem that we have here. We are trying to find the mass flow rate of the steam with all of this information. The next thing that I want to do is look at the first law and see what I can and cannot simplify as I solve this problem. So take a moment and look at that. There's my general steady state first law, and let's think about what things can we assume. First, let's talk about kinetic energy and potential energy. In this particular case, they've given us no indication that there's a change in pipe size, which could give us a change in kinetic energy. There's nothing about a height change, so I would assume, therefore, that it's safe to say that the change in kinetic energy and potential energy are 0. Okay. Now, in our previous problems, I've been able to get rid of the summation signs because I had only one stream in and one stream out. But here I have 2 in and 2 out. So I cannot get rid of the summation signs. What about work? Work requires moving parts. Okay? A heat exchanger is basically, the easiest one to understand is a pipe inside another pipe. There are no moving parts there. So in a heat exchanger, the work is going to be 0, or the power is 0. And what about the heat transfer? Now this one is a little bit more complicated because there is heat transfer happening. That's exactly what this is, right? It's a heat exchanger. Heat is transferring, in this case, from warm water to cold air. So there is heat transfer happening. But if my purpose for this device is to have all of the heat go from the water to the air, I really would rather not have it leave and go to the surroundings, correct? So therefore, the heat transfer to the surroundings is going to be 0. And in my equation, that's what I'm talking about. My system is defined, in this case, as the heat exchanger. Q is equal to 0. Therefore, I'm going to be able to get rid of this term. So what I'm left with is actually a really simple version of the first law. Right? The mass flow rate times the enthalpies of all streams in equals the mass flow rate times the enthalpies of all streams out. Therefore, I know that I'm going to need data for those enthalpies. The enthalpies for my air are given. We need to look it up for the steam. So take a moment, pause the video, and go look those up. Using the appendix in this textbook, I found that the inlet for the steam was 2870.7 kilojoules per kilogram, and for the exit is 2706.2 kilojoules per kilogram. If I look at this, the sum of mass flow rate times enthalpy at the exit, so I have the air at 45 degrees C, which is flowing at 50 kilograms per minute, and that's going to be multiplied by the enthalpy at that temperature, which is 318.7 kilojoules per kilogram. And the other stream exiting is this one. This was where the quality was 1, so therefore this is saturated steam at 2 bar, and that enthalpy is going to be multiplied by the unknown mass flow rate, m dot, times 2706.2 kilojoules per kilogram. This is going to be equal to what comes in. So we have air at 50 kilograms per minute, multiplied by that enthalpy, which was given, 308.7 kilojoules per kilogram, plus the unknown flow rate, m dot, times our water flowing in, 2870.7 kilojoules per kilogram. I have an m dot here and here. I can rearrange this equation and solve for m dot. $50 kilograms per minute times 318.308.7 kilojoules per kilogram over 2870.7 minus 2706.2 kilojoules per kilogram. Kilojoules per kilogram are going to cancel out, so my units will be in kilograms per minute. You can change those to something else if you like, but it's unnecessary. And using the calculator, I found that the mass flow rate of the steam needs to be 3.04 kilograms per minute. Okay, now I'm going to take a moment to pause here. We've got more of this problem that we want to do, but I am solving this system using the entire exchanger as the system. It is also possible to do this in another way where you break this up and look at the air side as a system and find the amount of heat transfer going in or out of that air, and that then would be equal to the amount of heat transfer going in or out, opposite sign, for the other. And I could split this into two separate equations if I prefer. Now there's a part 2 of this example. We want to now calculate the mass flow rate of steam required to heat 50 kilograms per minute of air if the steam exits as a saturated liquid at 2 bar. All that's going to do is it's going to change the exiting enthalpy of the water or steam. If you look this up for quality of 0, 504.7 is the value I found in the steam tables. And if you do this calculation, the mass flow rate with that number change is now reduced from 3 kilograms per minute to 0.2 kilograms per minute. Again, think about the fact that we've done a problem earlier this semester where we were doing going from saturated liquid to saturated vapor, and the amount of heat transfer for that was much, much more significant than any temperature change of the pure gas. So in this case, we're seeing that again, that to go all the way to liquid, that's going to suck up a lot of that heat transfer, right? And therefore, I need much less steam or water if I'm going to go all the way to saturated liquid. Okay. Now we have one more portion of this. We want to look at what happens if I fix the flow rate of steam to 1 kilogram per minute, then what's the specific volume of the steam at the exit? Fixing the flow rate of the steam is going to change the state of the exit. So let's write our energy balance again now, but I now know the flow rate of steam, but I don't know the enthalpy of the exit. Using the formula that we had come up with previously, but kind of rearranged it to group all the air terms and the steam terms together, I came up with this. If we solve this for H, it will have units of kilojoules per kilogram, and the value is going to be 70.7 kilojoules per kilogram. Okay, now, have I lost track of the problem? It was to find the specific volume. What this tells me is this helps me identify the exit state. Now then, let's go look at 2 bar with this enthalpy. All right, if you go to the saturated table, what you're going to find is that it is between, this enthalpy is between the liquid and the vapor enthalpy. So therefore, this is going to be saturated, so I need to find the quality. So the quality of the exit steam is going to be this 2370.7 minus the saturated liquid over the saturated vapor, minus the saturated liquid again. And therefore it's 0.8476. And this now tells me that the specific volume of the exiting stream is going to be the specific volume of the liquid plus the quality times the specific volume of the vapor minus the specific volume of the liquid. I guess I could have written that as a capital L like I've been doing. If you look those up, 0.001061 plus 0.8476 times 0.8857 minus 0.001061. Okay, and the specific volume of the exiting steam is going to be 0.7509 cubic meters per kilogram. So we've looked at how to solve a heat exchanger problem by analyzing the entire system at one time. And we've seen how we can find some things that were maybe unexpected, like the specific volume or density of the exiting stream based on this information. We're going to continue our study of steady state systems in the next video lesson. Thank you very much for your time.